Hello, this is Fahad from Game Code Bytes. In this presentation, I'm going to show you how to build a Slinger system with JavaScript, just like the one you see in this demo. I've seen this mechanism a lot in video games. For example, Angry Birds and Crush the Castle and many other games. So let's get started. To not waste your time, I created a simple boilerplate. I have a folder called Slinger, and there are 3 files within that folder: index.html, index.js, and style.css. Index.html, where I have the canvas and a reference to the style sheet and also calling the index.js. And I have the style.css file to put some styles on the canvas and on the body of the HTML document as well. And I have the index.js file where I'm calling the canvas by its ID, and I'm creating the context object to draw things on the canvas and setting the width and the height of the canvas, centering the canvas. And I also have 3 functions: update, render, and frame. Frame is going to call the update and the render, and then it's going to call request and frame in animation frame, and then calling itself. Then I need to call the frame function one time only. That's it. Now we need to create a circle on the canvas. You can call it a ball or a circle, it doesn't matter. So I'm going to create a new object called circle, and then you can pass X and Y and radius and color. Then we're going to set those initial values. And also we need velocity. It's going to be an object that has X and Y. And that should be good now. Now let's create a circle here. I'm going to center this circle in the middle of the canvas. 15 radius, and color is going to be orange. Now we need to render the circle. So it's going to be context.fill style equals color.color. Circle.color. Context.arc. That's how you draw a circle with the context object. .x radius, and it's going to be a full circle, 360 degrees, which in radian is going to be math.pi by 2. And we need also to say context.fill. Let's try this out. Nice. We have a circle. I'm going to refactor this just a little bit. Begin path. So close path. I'm going to set the line width, it's like the border of the circle, to be, for example, 5. And I'm going to add some sort of a border to that circle. And then the same drawing here should be good now. We need to stroke. Okay. I'm going to put some variables here, on constants actually. So we need gravity. Let's say 0.4. And I can also, let's save the mouse in an object, the mouse location. And I also need a point so that every time you press on the canvas, we're going to store the first point. So we're going to call it P1. And it's also going to have X and Y. And I need a variable called isMouseDown equals false. Now probably you can see those two lines, the mouse and P1, they're identical. And we can create a function that will return an object that has X and Y. Let's keep it that way. Now let's add some mouse listeners. So we need canvas.onMouseDown equals function. And what I need from that function is the offset X and offset Y, which is the mouse X and Y position on the canvas. And I can literally do for the rest of the on mouse up and also on mouse move. But I think it would be a good idea to use the on mouse up on the document instead of the canvas, because we want to disable so many things when the mouse is not down anymore. Now every time the mouse is down, when we click on the canvas, we want to set the isMouseDown so that it equals true. And also we need to keep track of the first point. So I'll say p1.x equals offset x, p1.y equals offset y. And I also want to set the circle X and Y position to the mouse X and Y as well. So I'll say offset X and circle.y equals offset Y as well. Now on mouse up, we want to say isMouseDown equals false. And we can keep track of the mouse position, saying mouse.x equals offset x, mouse.y equals offset y. Now also on the mouse move, we want to keep track of the mouse x position and y position, x and y. And also I want to say if isMouseDown and circle.x equals offset x, circle.y equals offset y. Now what we need to do is that we render a line every time we press and then we drag. We want to render a line instead of what's happening now, because we're setting the position of the circle based on the mouse X and Y position. And also we need to clear the canvas every time on every frame. So to get rid of this issue, we will go to the render function, and then we'll call context.clearRect 00 width and height. Now this is probably not the best practice to clear the canvas on every frame, but for the sake of simplicity, let's just keep it that way. Now I probably mentioned that we need to draw one line, but in reality we're going to draw two lines. Because if you think about the Slinger, and just like the demo video I showed in the first minute of the series, there are two lines, two cables, or two cords. They're coming from one point to the right side and to the left side, just like that. So let's start drawing the two lines and add the logic relevant to that. So I'll say if isMouseDown, let's create the direction, the angle, which is going to be the direction from the first point. The moment we press something, we press on the canvas and then we drag. This is going to be P1. And this is going to be the mouse position, the last position we want. So the direction is going to be math.atown2, actually p1.y minus mouse.y and p1.x minus mouse.x. That's how we get the direction. And then let's get the cosine, which is the x component of that direction. We do the same, but here it's going to be sine. Also, we need an equals here. It's going to be sine. Then we need to create the new x position. Let's just call it x equals the p1.x plus minus sine multiplied by circle.radius. And here it's going to be the cosine, and this is going to be the y position, because this is going to be the p, this is going to be the position, the center of the ball, and we want the perpendicular vector on this point. So clockwise and counterclockwise. So the first one, for example, is going to be here, and the second point is going to be here. So from here and here, we'll draw the chords. That is the logic behind it. Now we'll draw a line. I can create a function to draw a line. That would be easier, I think, and more readable, let's say. So we'll go here, for example, and say function draw line, and that function is going to take x1, y1, x2, y2. And then we need to context dot begin path, context dot stroke style, for example, let's say 888, context dot line width equals 3, for example. Move 2, it's going to be x1, y1, and then line 2, it's going to be x2, y2, context dot stroke, and context dot close path. Now we need to draw a line. So the moment we press or we click the mouse on the canvas, we will calculate, or not calculate, actually we'll get the position, the x and y position here, and then we drag, and then we will keep track of the second point as well. So we need to do this logic here and say if is mouse down, then I need to draw that line. So I'll say direction is going to be math.atown2, and it's going to be p1.y minus mouse.y, p1.x minus mouse.x. And what we're doing here is we're getting the direction from P1 to P2, or the mouse position here, the angle or the direction. Next, we want to get the x component of that direction through the cosine. So I'll say math.cosine the direction, and we need to get the y component by using, the sine. So it's going to be sine direction. Then we're going to draw the line. We'll say draw line, and I'm saying draw line, but we don't have this function. So let's create this function. Function draw line, x It's going to take x1, y1, x2, y2, then context.begin path, context.close path, and then we can say context.stroke style equals, for example, in context.line width equals 3, context.move to x1 and y1. That is the first point of drawing. And next is going to be line 2, like this. And last we need to say stroke. Now we need to go back and continue drawing the line. So here we'll say p1.x and p1.y, and the second point it's going to be the mouse.x and mouse.y. Let's test this out and see if it's going to work or not. Nice. We were able to draw a line stretching the chord. Now we can draw the line based on the ball or the circle. Now we need to add the physics so we can drag the ball and then we throw it in the air. So to do that, we will go back to the update function and also say if is mouse down. Then we need to calculate the direction from the first point and the second point, which is going to be the mouse or even the circle itself. So we can throw it in that direction. Now let us explain the physics behind the Slinger simulation. So what is going on? We have the circle here, or the ball, or whatever object you want to throw using the Slinger. The moment you clicked, we're going to store this mouse position as a P1 point. Let's call it P1. And we're going to have the X and Y position of this point. Then we will drag the circle like this. Now we need to represent this by having a line from here to here. This is the first point, and we drag the circle until here. Now this is going to be the second point, which is the mouse X and Y position. Now once we have these two values, that's all what we need, because now we know the magnitude, how much power we want to throw the ball with, how much energy we want to use to throw the ball with, and also we have selected the direction or the angle we want to throw the ball with. Now the physics is going to be like this. We're going to calculate the x dx position, the difference between the circle's x position and the first point x position, and we also need the dy, which is going to be the difference between the y position of the circle and the y position of the first point. This is going to be dy, and this is going to be dx. Now we can use the Pythagoras theorem, which is one of the formulas we have used in previous tutorials, to calculate this magnitude, which is the distance. Now we have the magnitude. Now we can use something with JavaScript called atan2 to calculate the direction, to know exactly the angle we're throwing the ball with. And that function is going to be used like this, math.atan2, and then you pass dy and dx, and that's it. So we need to get the dx first. Now it's p1.x, and then same goes on dy. Then we calculate the direction by saying math.atan2. It's going to be dy dx. Then we'll say circle.vil.x equals math.cosine the direction multiplied by the distance but we don't have the distance, so we have to calculate the distance as well. And the distance is going to be the magnitude of the vector. The more we grab, the more we drag the cable, the more power we have. And we'll go back to the Pythagoras theorem to calculate the distance or the magnitude of that vector. So we'll say math dot square root dx by dx plus dy by dy. Then we multiply by d, and we need a little bit, we need to give a little bit of small number to d because d is going to be a big number. So we can manipulate this and you'll see the results. We can do that later on once we have all of the logic set up. And then we'll do the same for the velocity on the y-axis, but we need the sine here instead of the cosine. Okay. Now this logic was for if the mouse is down. Now if not, we'll say circle.vil.x multiplied by 99 just to add some friction to it on both x and y axes. Then we'll say circle.vil.y plus equal gravity, because we also need the velocity on the y-axis to be affected by the gravity. Let's make sure we have gravity. Yes. Then we'll say circle.x plus equals circle.vil.x, and same goes for the y-axis. Okay. Let's test this out and see. And we have an error here. And it's on line 37. It's a typo, so it needs to be dy. Okay. Now, as you can see, something's wrong here. It's because we're setting the direction to be like this. It's like I'm pushing this circle here, but instead we need the exact opposite. So to fix that, we need to come back here and say I need the opposite of the velocity, and this should fix it. Good. Now we need to fix another issue, which is the fact that every time I throw the ball, it will go outside of the canvas. And to do that, we need to make sure to reflect the velocity on both x and y axes every time it hits one of the borders of the canvas. So let's fix that. In the update, I'll say if circle.x minus circle.r, which is the radius, is less than 0, or circle.x plus circle.r plus, greater than the width, I'm going to reflect or reverse the velocity on the x-axis of the circle. .vil.x multiplied by -1. And same logic goes on the y-axis as well. But here is going to be the height as well. And the velocity is going to be on the y-axis. Okay? Good. There is another issue we need to fix as well. Every time the circle bounces on the ground, it will keep pushing itself because the velocity, it will keep increasing on the y-axis because of the gravity. And to fix that, we'll say if height minus circle.y minus circle.r multiplied by 2 less than negative circle.r, then we'll say circle.y, we're just repositioning the circle. Height minus circle dot r. Let's try this out. And it's fixed. Now the Slinger simulation is working perfectly, just like how we needed. But you might notice in the first minute of two in the video, I used to have like 2 cables attached to the circle. And to do that, we need to do a little bit of refactoring here. So let's do it. So what do we need to have those cables attached to the circle? It's going to be almost the same logic, except when I drag the circle here, I mean, the line should be here. One of the lines should be here, and the other one should be here. And this should be work if we can calculate the perpendicular angles or perpendicular vectors of this point, like this first point. We'll get this one and this one. So let's do it. We go to the render function and we fix that. Now we have the direction here, and we have the cosine and sine, which is good. So we need to calculate the new x, saying new x, and actually let's reuse this variable. So we'll say new x equals center x. Oh, we don't have center x. We can just say p1.x plus minus sine multiplied by circle.r. And then new y is going to be y, and this should be the cosine. Now we can draw the first line like this, saying I want to draw a line from new x, new y, and then mouse x, mouse y. Then we can do the same calculation to get the other vector, the other perpendicular vector, but on the exact opposite side. But here we'll say sine, and this is going to be minus cosine. And then I'll do the other drawing here. So let's test this out and see. And it's working. It looks more realistic now. We have the slinger. It looks like it's attached to something. And then we keep dragging the ball, and then we throw it. Now, everything looks good, but we have another issue. If I drag the circle here and try to go outside of the canvas, it's going to stuck there. So we need to fix this. So probably create a function called push, for example, or reposition, whatever you want to call it. So let's go up there, and then we create a function called push. And then here I'll say if circle.x minus circle.r less than 0, I want to do this. Circle.x equals circle.r, maybe plus 3. And then circle.val.x 0, circle.val.y equals 0, and then also is mouse down equals false. This is going to handle that issue on one of the borders, which is this one on the left. Let's try this one, and then if it works, we can do it for the other borders, the top, the right, and the bottom. So let's test this out. Drag it, and it didn't work. Let's see why. Of course it didn't work, because we did not call this function. And where do we need to call this function? It's on the on mouse move. So on is mouse move, on mouse move, within the is mouse down, we'll always call push. Let's try it. And it's working. Now we'll do the same logic on the other borders. So I added the rest of the logic. It's almost similar to the first one, but I just don't want you to watch me writing the code and take some time to do it. So let's test this out now. You drag it, and if you try to go outside of any of the borders, it will set the velocity to 0 on both x-axes, and is mouse down is going to be false. Now I'm going to do a small refactoring and create a function to hold at least these 3 lines of code, setting the velocity to 0 on x and y, and setting is mouse down to false. You can call the function whatever you want. I'm probably going to call it reset. And then I'll take this logic here, put it here, and then I'm just going to call the reset function instead of those 3 lines. And it should still work. Yes. Good. Now there are some small details I want to explain and at least change those numbers to show you what's going to happen. For example, here, if I change this to, let's say, 4, and I'll try to drag it, it's going to be more aggressive. So putting a small number is going to make it seems reasonable. And the other thing is the friction I'm adding here. For example, if I use 9, you will see what's going to happen. You see? There are more friction on both x and y axes for the velocity. We'll put this back to 99. So also you can have those in variables or constants. For example, friction. And let's do that. Let's create a new constant called friction, 0.99, and then just change this to friction. Okay, and it should still work. And the other one you can change is probably create a constant called sensitivity or whatever you want to call it and put it here. So you don't have to keep changing it on these 2 lines of code. You can just create a constant here and then use it in here. Or you can call it aggressiveness, whatever you want to call it. But now the simulation is working just like how we expected it. All right, friends, this is going to be the end of the Slinger Simulation with JavaScript tutorial. If you find it useful, subscribe to my channel. It's called Game Code Bytes. As you can see, there are a lot of potentials of video games you can build just based on those mechanics. And you can also translate it to a mobile game, but instead of using clicks, you will use touches. Stay tuned for the next video. Thank you guys for watching. This is Fahad from Game Code Bytes.